Welcome back. So we will start looking at feedback interconnection of dissipative systems, right? But this is the first time we actually want to look at feedback control systems in a formal fashion. We kind of hinted in many times, basically somewhere control is there, and then in fact control is the reason why we study all these techniques and things like that. So we will pose basic problems in control and things like that. That's the first part of the lecture, and then the second part is actually where we go back to the topic of dissipative systems and look at feedback interconnection of dissipative systems, right? So that's the second part of the lecture. So the first part is basically feedback control systems, and then as usual we'll start with linear systems, just because it provides always some simple solutions and simple understanding of the main concept. So we have this x dot equals ax plus bu. So by now we understand what kind of system there is. The question of stabilization, or in other words, this closed loop system is stable, which we referred in the last few examples and things like that, but essentially boils down to saying that can we find matrix K such that u equals kx is stabilizing. That means I'm going to basically let u equals kx, and then in the closed loop system x dot equals a plus bk times x, and then we want to see if that particular closed loop system is has a stable, asymptotically stable equilibrium point, which is essentially equivalent to saying a plus bk is Hurwitz, right? This is the most basic problem, and other questions that should come into your mind are, why should we be looking only for linear control systems, right? I mean, we have a linear problem, x dot equals ax plus bu, and then we are looking for a linear control law. But in reality, we could actually look for nonlinear control laws. U could be some phi of x, right? Perhaps we are trying to minimize some kind of performance measure, and the optimal answer could be nonlinear, right? So that's something that one should keep in mind. But this particular problem statement is actually about finding a linear control feedback for this particular system, right? And of course, a more interesting question, and I'm going to leave all these questions for you to explore, Google search them basically. If there is a linear system for which we can find a nonlinear feedback law, does it automatically imply that there is a linear feedback law, right? So keep that question in mind. In other words, I'm saying basically, can you find an example where the only way to control a particular system, a linear system, is by considering a nonlinear feedback, right? All those questions we should keep that in mind. But this problem is about basically finding linear control law, and that boils down to finding this particular K, right? So this is basically what we call as full state feedback problem, where basically the feedback u, the control, is going to depend on some matrix times the entire state, right? But alternatively, we can actually consider something called output feedback, and it's important for us to understand the difference between these two. If we have a system and we are assuming for a full state feedback stable controller, we need the entire state is measurable. Each one of the state is measurable. So for example, in the worst case, if somehow this linear system is an approximation of a PDE, and that comes, for example, in airplane surfaces, for example, you have a structure that is continuous, and then it's interacting with wind, and every point on that is part of your state. In other words, an entire function is part of your state, and then you should be able to measure every one of those things, right? And that is almost impossible in most practical scenarios, and though the problem is easy to state in terms of full state feedback, right? So therefore, we always have to go back to some kind of output feedback control law, and where output is Cx plus du. In many cases actually it is simply Cx, but sometimes it could be a combination of both state and control input, right? This is where the measurements happen. So therefore, one way of connecting these two problems is basically, somehow if I can reconstruct the entire state of this x through y, right, then we can go back to the answer that we got from the full state feedback and then basically solve the problem as if it is a full state feedback. And that kind of technique is what we see in very classical problems, and the most famous of them is basically Kalman estimator. We can estimate the entire state and use that estimate for in a feedback, and then basically we get some kind of control by just measuring the output. But through Kalman estimation we can estimate the entire state, and then that is useful for feeding back and using the full state feedback stabilizing controller. But in reality we don't have that access to the entire output, so on entire state. So we can state this problem directly in terms of output stabilization, where we try this to find this k such that u equals ki is stabilizing. And you can plug in and then say the closed loop is going to be this a plus bk times I minus dc inverse c is Hurwitz. It may look complicated, but when you actually substitute and solve it, it's not a big deal. So there are concepts of controllability and observability and things like that. So in the first case all we need is controllability to show that you can always find a k. Actually, you don't need even controllability, you need something called stabilizability, but details we're not going to get into. In the second case, we may need actually observability for estimating the entire state, and use that. Through controllability or stabilizability we can stabilize, right? So in other words, basically if you have an output feedback control problem, then you need much more than simple controllability, as in the case of full state feedback or stabilizability. We actually need something more, you need observability through this output and things like that. So that's why if you go open any of the linear systems books, basically the standard assumptions will be that this system is going to be both observable and controllable, right? Anyway, so these are the two problems that we can talk about. So here we considered essentially static feedback. That means u is just dependent on current value of x, but in reality we may gain advantage through considering dynamic feedback, where u depends on current and past values in terms of some kind of integration and things like that. And that's stated very well in this fashion. So does there exist another set of differential equations written as the differential equation in front of you, x dot of c is equal to ac times xc plus bc times y, and u equals cc times x. So the output of the first system is basically going to enter the second system, and the output of the second system is basically going to become your feedback controller. So can we find AC, BC and CC such that the closed loop system is stable, and then the closed loop system looks something like this, right? So this is a very standard problem of finding dynamic controllers. And again, none of these are that easy to solve, but they're not that complicated. There are multiple ways of approaching this, and I'm going to basically show a solution for the full state feedback, and leave it as a homework for you to basically explore other aspects. We won't learn as much in this particular, for this particular course where we're dealing with primarily nonlinear systems, but it's actually good to know some of those techniques. Anyway, so we want a case as that a plus bk is Hurwitz, and we have seen by now we should be familiar that that's nothing but looking for a Lyapunov function of x transpose px such that this inequality is satisfied, right? Which is a if we didn't have k and it's just checking stability of a, then that becomes a linear matrix inequality in the matrix P, and that's easily addressable. But here we have two variables, P and K, and as you can see, basically we have terms like P times B times K. So a term that involves both P and K, and it's a nonlinear inequality, and of course the two variables, and I believe they are called bilinear matrix inequality simply because if you hold on one thing, that it becomes linear in the other variable and things like that. So one way to perhaps check this particular condition is pick some P and then solve for K as an LMI, and then get that K, plug it in, and then solve for P, right? I mean, if the first P satisfies all the conditions we need and K satisfies all the conditions we need, then that's it. But on the other hand, that may not be the case. We pick some arbitrary P and then initiate the algorithm, and then basically go back and forth, and then bilinear matrix inequality satisfies this very interesting property that if you hold on one thing as a constant, the other one is linear. So we can solve that problem, but there's no guarantee such iterative process actually converges. So there is this ingenious solution. I don't know who came up with first, but you'll find in many of the standard books on linear matrix inequalities for control, is you can rewrite this as the transpose problem, and essentially that's looking for some other matrix Q and K. K is still there. A plus BK Q plus Q times A plus BK transpose less than 0. So this is still bilinear matrix inequality, but what's nice is when you actually expand it and define X equals K times Q, it becomes linear matrix inequalities in two variables, Q and X, some new variable X now, right? So look at the comparison between the bilinear matrix inequality and this one. The bilinear Q and K are there, and it is not linear in both Q and K, right? But by replacing KQ with X, it becomes suddenly a completely linear matrix inequality in Q and X, right? And by solving this, we can basically solve for Q and X, and we'll get Q and X, and hopefully Q is invertible, and then therefore K can be solved as X times Q inverse. And this is a beautiful technique to solve for full state feedback, right? So unfortunately, as you can see, these are these things evolved as tricks of the trade rather than some standard procedure and things like that. But once we realize that this is one way of looking for full state feedback, and becomes one of the best ways to actually look for full state feedback, right? So unfortunately, if you have output feedback problem, there is nothing as simple. You will end up with at least bilinear matrix inequality. If not, it won't become more complex than that. And then the iterative algorithm that we discussed for any bilinear matrix inequalities, do not have any guarantees of convergence. Another way of solving it is actually the standard LQG actually solves a dynamic feedback problem by actually minimizing some functional, which we'll talk quite a bit at a later point. Not necessarily the dynamic part, but the performance measures and things like that. So, but LQG is one of those beautiful results that actually considers both output feedback and optimal control in one single shot, and then it gives a very nice equality solutions rather than LMI as we have here. But then interestingly, we have a solution for some kind of solution, if not the best solution for a dynamic feedback problem. We have full state feedback problem, but output feedback problem of the static nature has no simple solution. So if we extend this logic to nonlinear systems, basically we will consider x dot equals f of x comma u, some nonlinear function of both x and u. And the problem of finding stabilizing control or full state feedback stabilizing control is finding some phi of x, and then putting that in u, and then hopefully f of x comma phi of x has 0 at the origin, and that 0 happens to be asymptotically stable, right? And therefore, you can imagine this is so much more complicated, and we probably should give up at this point in terms of finding a generic theory. And then we do. I mean, next several classes I will show you various techniques for classes of nonlinear systems, but nothing, no single theory that works for everything in a clean fashion, right? So in fact, the control problem is so difficult in nonlinear systems, it remains to be in some sense a very open problem. And there are a bunch of techniques. Each one of those techniques should be known to any student of nonlinear control and use as and we need it, right? And then by knowing the details of the techniques, one can actually invent new techniques, and therefore the focus of this particular course has been in terms of understanding the insights into the background of some of these results, though not always every step is proved here, but at least the insights are given to the proofs, right? Anyway, the output feedback problem is very similar to linear. Instead of x dot equals f, we'll have additionally output y, which is a measurement, h of x comma u, both dependent on both state and output. And then of course the problem of output feedback is simply finding this function phi of y rather than x, which is stabilizing, right? So neither of these problems are simple enough, and of course we can therefore venture and basically state the problem for dynamic feedback, and again it's not easy, and the statement is quite similar to what we have seen in the linear case. And in all these cases, of course, if we linearize the system and we manage to find linear solutions, then we can use the full state feedback, the linear solution or the LQG solution for the dynamic controller. But then that will give you only local solution, and many times that's a good starting point, and then hopefully we solve some local problem, and then somehow move from that local problem to the next point, and then next point, and so on. And that's a very typical standard technique for nonlinear systems. So let's actually perhaps see some examples. So if I have something like x dot equals minus x cube plus u, okay, plus x cube. It turns out that this is essentially nonlinear system. You can actually pick u equals minus x and then solve this particular problem, okay, and you'll get a locally stabilizing. On the other hand, we can actually pick u equals, I don't know, minus 2x cube, right? If I pick u equals minus 2x cube, then basically you can see that Vx equals half x square. V dot of x is going to be equal to xx dot, which is going to be xx dot, times x cube plus u is minus 2x cube. So I'm going to get minus x power 4, which is less than 0, showing asymptotic stability. But let's try to understand. So I have something like x dot equals f of x plus g of x times u, okay, more generally, right? The generic version f of x comma u is quite difficult to handle, and we won't typically have the courage to address that particular problem. But if we have some system where it's affine in control, right, then can we say something? In the above example, basically what we did is u, somehow by knowing the uncertainty, the nonlinearity, we cancel that nonlinearity. So this is called the technique of nonlinear cancelling the nonlinearity. Okay, or also it's called, well, it's not in this particular case. In fact, let me go back and then basically show you one more this thing. So let's say x dot equals x cube plus u, right? That's what we considered. I showed earlier u equals minus 2x cube, but instead I could have chosen basically u equals minus x cube plus minus 2x, and the closed loop system becomes linear. We x dot equals minus 2x, and in this particular case we can actually choose v of x as half x square, and then v dot is going to be simply minus 2x square, giving us exponential stability. Okay, how did I suddenly get exponential as opposed to asymptotic stability? Simply because it satisfies those nice upper and lower bound of the Lyapunov function that we had in exponential stability. Anyway, it's not so important. So what this essentially shows that I can actually, if I have some system like this, I can choose this u to cancel the nonlinearity and make the closed loop linear by adding a linear component, right? So this technique is called as feedback linearization technique. Okay, so it's a nonlinear problem, but then we can make the closed loop linear, right? So if we actually consider the more general problem of this nature, okay, and then assume g of x is non-zero, okay, for all x, then I can again pick u equals minus g of x inverse, okay, f of x plus some k times x, where k is negative definite or something like that, okay. So then basically we can show that the closed loop is going to be x dot equals kx, and then k can be chosen appropriately for the system to be stable, and therefore we get exponential stability. The problem is basically this assumption, okay, the x in in the vector case, basically essentially u can be chosen as minus g inverse of x times f of x, okay, and plus some k times x or something like that, right? So from a technique perspective, feedback linearization works if this g is somehow invertible, right? If it is not invertible, then basically the people basically approximate that g inverse with something that is closely imitating inverse and things like that, and hope for the best and things like that, right? So it's a technique that cannot be thrown away, but at the same time it may not be the best technique for one single reason, that let's say f of x in the earlier example, something like if f of x dot equals minus x cube plus u rather than plus x cube, then u could be chosen to be 0. You don't have to do a feedback linearization in this particular case to get global asymptotic stability. Perhaps if you want some better performance, we can put u equals minus x or something like that and get better performance. So what that means is basically the nonlinearities that are good in nature, that are stabilizing in nature, you are ignoring them and cancelling them, all of them. And so therefore cancelling the nonlinearity blindly, even if this condition g is invertible and things like that, is not the best thing to do. And anyway, I mean, if G is a rectangular matrix, then we take pseudo inverse and things like that. All kinds of fixes are there. But in general, basically, for full state feedback control in nonlinear systems, the most generic technique that you would see, that people kind of recommend is this feedback linearization under certain conditions. And then there are beautiful theories. I mean, I may get back to this particular technique at some point in later lectures, briefly mention some of them. Basically, the question is, can we transform some kind of problem x dot equals f of x comma u, or even f plus gu into a feedback linearizable form, right? Okay, so what I mean is basically not always we can find this invertible g and things like that. Is there a simple technique that not simple, is there a nice justification for feedback linearization and things like that? And once we kind of know that the something exists, then searching for such a controller is much better than much easier than actually finding them in the dark and things like that. So there's this entire technique that's based on differential geometry. Okay, you will hear some of these things as basically Lie groups and Lie derivatives and things like that, and using the concept of this, coming from differential geometry, people actually developed an entire class of nonlinear control designs techniques that essentially boils down eventually that can be moved into this realm of feedback linearization. right? And you'll also hear things like differentially flat systems and things like that. There are some wonderful theories there that we will not be covering in this particular course, but essentially the nonlinear control is so complicated that every technique is useful, and we may hint towards some of the these techniques, but not really much more than that. Okay, so one classical book is by Albert Isidori on these Lie derivatives, and then there are many newer books that came in. Richard Murray from Caltech has done wonderful work on flat systems and things like that, right? So anyway, the summary of this entire discussion is essentially to understand that nonlinear systems, even full state feedback is not an easy problem, and any number of techniques is useful. And then we will actually take a pause and then come back and talk about not directly control but feedback of dissipative systems.